Hi, everyone. I'm Catherine. I'm a research associate at ECS. Currently, I'm supporting the statistics division at NOAA Fisheries. Today, I'm going to present how to use machine learning to improve survey design. In today's talk, you will learn how we build a model from the ground up, including selecting features, training many machine learning models, and we will pick two winners. And from that two winners, we do a model assembling. And then we predict recreational fishery behaviors. And from that, we decide a new survey, and we will analyze, compare with the previous survey, and see how much we get improvement from the modeling. Before I jump into math, I would like to talk a little bit about myself. I have a biology training for background. I studied jellyfish for my PhD, but during the process, I wondered, besides fulfilling my curiosity, could I solve a real world problem? Could I make an impact? So I decided to go do a Canals Fellowship at NOAA for 1 year. During that year, I learned how to incorporate science into policy. And that experience totally changed my life. I established my career goal after that fellowship. I wanted to bridge in the gap between science and policy. And to be specifically, I would like to bridge in the gap with data science. That's why I become a data scientist. For example, the overarching goal of NOAA fishery is to promote productive and sustainable fisheries. That sounds very straightforward. But in order to do that, we actually need a lot of data. We need to know how much fish are still in the ocean. To do that, we need independent research. We also need to know how much fish we catch. So we need data from both recreational fisheries and commercial fisheries. My part in this process is to support recreational fisheries. Recreational fisheries are actually more lucrative than many people would think. Every year, there are more than 8 million people taking more than 200 million trips in the United States, and the economy impact is more than $70 billion. If the recreational fishery is a one single employer, that would be the third biggest employer in the United States, following Walmart and Amazon. That is how lucrative of recreational fisheries. Every year at NOAA, we distribute more than 300,000 surveys along the 17 East Coast. And the response rate is more than 30%. Each survey also looks very simple. It actually has complex thought behind it. I used to belittle per paper survey because comparing with high frequency satellite data and automatic underwater vehicle like survey the ocean, a paper survey seems very humble. But actually, there's one big differences between survey human and monitoring environment. The people have free will. That increases the complexity of getting the real number. For example, from this survey, you will see the first question is asking, where did you get weather information? Why we are asking about fish? That is because not every people fish, not every person fish. But if a person who doesn't fish get a question asking only about fish, then he probably will feel the survey is irrelevant to them. And the survey probably will just throw into the garbage can. But if we only get the data from people who fish, then the estimation will way much higher than the real number. That's why we put different questions into the survey and try to engage with our audience. We encounter a challenge while doing the survey because the fishers with or without license living everywhere. If we just do a random sampling, then we will need a lot of sample size. That means very expensive. So the way to combat that is to do stratification sampling. Currently, we're using whether they're having a fishing license or they live in coastal or non-coastal zone. But here comes the questions. Is a coastal zone a fixed area? Will that be different among different states, or will that be different among different seasons? That's the way we try to do the research and try to improve our current stratification. We try to build a model to predict whether people will go fish or not. In other words, we try to find a fishing likely strata. We include a boat ownership, fishing license, distance to the coastal line, and the population of that county residency. Also, we include the survey time and the year and the state. We also include whether that person has a phone line. The data has 5 years observation. Each observation has boat ownership, license status, and we calculate the distance to the coastal line based on longitude and latitude. And we also crosswalk with 2019 US censorship to get the population numbers of that resident county. The first step is to select predictive features. The method we use is random forest with Baruta algorithm. The Baruta algorithm is basically creating a random shuffle data set and then build a random forest model from both the shuffle data set and the original data set and comparing the feature. If the feature we selected from the training data set actually is not much different from the feature we got from the shuttle data set, then we will say that feature is not very predictive. In the other way, if the feature, the differences is very big, then we will say that feature is very predictive. Sometimes we will encounter not only the feature is not only similar, but could be less than the random data set. Then if we include that feature, the result probably will be misleading. So here's the result we got from this random forest and Baruta algorithm. The license status is most predictive featured in our model, followed by the distance to coast and the boat ownership. We also include the survey state and the time of the survey, and also the population of county level. But we also found that the landline is not very predictive. It's not much different from the random data set. So we exclude the features from our following models. And then we train many different machine learning models, including different kind of decision trees, random forest, discriminant analysis, neural networks, and regular regression models. Each model is trained with 10-fold cross-validation and repeated 3 times. And in the end, we pick 2 winners according by their accuracies and kappa. We picked XGB DART model and C50 trees. The XGB DART model means extreme gradient boosting tree model. It put different weight from the decision tree. The earlier of the branch, weight heavier. We also remove comparatively small branch to make sure the model is not overfitting. The C50 tree has similar concept. It balances the information gain and model complexity to make sure it's not overfitting as well. And both models have accuracy higher than 83% and the kappa is around 0.4. And then we train 2 localized models for each of the state, 1 XGB model, 1 C50 models. And then we compare the modeling results with the general model. Most of the time, the localized model wins because it's more tailored to the local situation. But sometimes the general model stand out because it has more training data set. And we will use a winning model, either local or general model, to predict the fishing behavior. Here's the result. The y-axis is the distance to coastal line, and the x-axis is the survey period. We have 6 survey period during the survey. So we have a survey every 2 months. And the column is the license status, whether it has a license or not. And the row is the boat ownership, whether it has a boat or not having a boat. And the color indicate fishing likelihood. Red color means very likely to go fishing. Blue color means very unlikely. And the bubble size means how many observation I have from the training data set. The bigger the bubble means I'm more confident with the prediction results. From here, you could see if without a fishing license, then it's very unlikely to go fishing, no matter how close to the coastal line or having a boat. That's coming from that the fishing license is really very predictive. And with having a fishing license, the boat ownership makes differences, especially during the winter time. You could see that during the summertime, people are more willing to travel further to go fishing. But during the winter time, only people who has a boat still go fishing. And the differences between the XGB model and the C50 model is the XGB model is more aggressive during the winter time, but during the summertime, it actually predicts people are willing to travel further for fishing during summertime and become more conservative during the winter time. The fishing likely zone become very close to the coastal line. But no model is perfect. That's why we combine the results from different models called ensemble modeling. Here is the result from ensemble modeling. It's still in general, people without fishing license are unlikely to go fishing, and people with license and boat are more likely to go fishing, especially during summertime. They are more willing to travel further. And during the winter time, the fishing likely zone become very close to the coastal line. And through ensemble modeling, we get a more robust result. I also want to emphasize one thing is the importance of having boat information. The current design is not including boat ownership, but if the boat ownership is not important, we should see from the right figure where the y-axis is fishing likelihood and the x-axis is the serving time, but the color become the distance to coast. So if the boat ownership is not important, we should see the color change from red very smoothly to blue. But when you see the right-hand side panel, the license group, and during the summertime, you can see the color change from red, yellow to blue, yellow, until it turned completely blue. Those yellow bloods in between the color, that is the influence of having a boat ownership. That indicate that just having a fishing license and distance is not enough to predict their fishing behavior. So we cut a new boundary from a new model. The second column of this table is current boundary. You could see it's comparatively more rigid. During the winter time, it's 30 miles from the coastal line. During the summertime, it's 65. The new boundary from the model is more dynamic with the season. During the winter time, the fishing likely zone is actually extremely close to the coastal line. And during the summertime, it goes further off coast. And we compare the new design with the old design by reanalyze each observation. And we found more than half of the time, the new design showed improvement. So here's our recommendation from the model. So besides including the state and time of the survey, we recommend also include boat ownership when deciding the stratification sampling. And we also recommend to consider a third flip coin stratum. So instead just sufficient likely and unlikely, there might be a third like middle ground, like flip coin stratum. That could be very useful, especially for a bigger state like North Carolina. The future analysis, we would like to continue to improve our auxiliary variables. For example, currently the time of the survey we use is just wave, like 6th wave of the month. But the wave means different in different states. For example, the southern state may have less seasonality and the northern states may have more seasonality. And even for just for summertime, there could be differences in different years too. So I would like to replace the wave by temperature so that the prediction could be more realistic and reflect the weather at that year. And also I would like to refine the license match. The current license match is just mean that person has sufficient license within the 2 sampling months. But there could be a licensing renewal gap. So maybe we could expand the temporal period to 1 year. So as long as that person ever have a fishing license within a year, then we'll consider that as a license match. Also, there are many different kind of fishing license. In some states, the fishing license is actually combined with hunting license. So we would like to refine our license definition and see if that improve our modeling. But the overall take-home message is machine learning could be very useful, not only to improve commercials and help making money, it could also help protecting the ocean. I would especially like to thank my colleague at NOAA, Fishery Statistic Divisions, who helped me build a model, and also RTI, who did the groundwork of collecting samples. I would also like to thank my coworkers from ECS, especially the AI Center of Excellency team and the communication team, who really polished this presentation. Thank you. I'm ready to take questions.